Today we're doing section 6.2, Antidifferentiation by Substitution. Indefinite integral. The family of all antiderivatives of a function is the indefinite integral of f with respect to x and is denoted by an integral f of x dx. If f is any function such that f prime of x equals f of x, then the integral f of x dx equals f of x plus c, where c is an arbitrary constant called the constant of integration. Let's look at example 1. Evaluating an indefinite integral. Evaluate 2x minus cosine x dx. And there should technically be parentheses around that. So this is the derivative here. What function gives us the derivative 2x? And you should be saying to yourself, x squared. And then what function gives us the derivative cosine x? So what function did we take the derivative of to get cosine x? And you should be saying sine x. And then you would have a plus c. So that's what you're thinking. You're going backwards here. This is the derivative. What did we previously have to get this? Properties of indefinite integrals. So the constant k of an integral k f of x dx can be factored out, and then you can take the antiderivative of f of x. Also, when I have the antiderivative of a sum or difference, I can take the antiderivative of the two terms of that sum and difference separately. With power functions, you have a power rule. So when I have some function to the n, all I do is add 1 to the exponent, divide by that new number, plus c, where n doesn't equal negative 1. If n equals negative 1, then my antiderivative would be of 1 over u du, and that would be the natural log of the absolute value of u plus c. Trigonometric formulas. The antiderivative of cosine u is sine u plus c. The antiderivative of sine u is negative cosine u plus c. The antiderivative of secant squared u is tangent u plus c. The antiderivative of cosecant squared u is negative cotangent u plus c. The antiderivative of secant u tangent u is secant u plus c. And the antiderivative of cosecant u cotangent u is negative cosecant u plus c. Exponential and logarithmic formulas. The antiderivative of e to the u is just e to the u plus c. The antiderivative of a to the u is a to the u divided by the natural log of a plus c. The antiderivative of the natural log of u is u times the natural log of u minus u plus c. And the antiderivative of log base a of u, you would use the change of base formula, natural log of u over the natural log of a. And then you would take the antiderivative, and it would be u natural log of u minus u all over the natural log of a, since that's a constant, plus c. Let's look at example 2, using substitution. Evaluate the antiderivative of x squared e to the x cubed dx. So here we have some function, and we can't take the antiderivative because it's not just an x, okay? So this is sort of like undoing the chain rule, okay? So what we're going to do is we're going to look at this, and I'm going to take my exponent of my e, and I'm going to let that be u. So u equals x cubed, because I want to get this in the form e to the u. Okay, then I need to take the derivative of this, because all of this, instead of being in terms of x, I'm going to write in terms of u. So I would have the derivative of u is du, would be 3x squared dx. Now I notice I do have an x squared here, so I'm going to be able to replace this x squared with whatever equals here, but I only want x squared dx, because notice I have x squared in dx. I need to get rid of that 3. So I can take and multiply both sides by 1/3 and have 1/3 du equaling x squared dx. Therefore, this integral would now become, based on my substitutions, 1/3 du times u, or e to the u. So 1/3 du was for the x squared dx, and then this x cubed became u. What I'm going to do is I'm going to rearrange this. Okay, so I'd have 1/3, I can factor out that constant, e to the u du. The antiderivative of e to the u is just e to the u, so this becomes 1/3 e to the u plus c. And then I replace u with what it was, because I want to evaluate it in terms of x. So 1/3 e to the x cubed plus c. And that would be your answer. Let's go ahead and look at another one using substitution. Evaluate the antiderivative of 6x times the square root of 1 plus x squared dx. So usually with problems like this, you're always like, what do I let u equal? Usually it's something that can be written in parentheses is what I let u equal. So here, we're going to let u equal 1 plus x squared. Now I take the derivative of u, and I'd get 2x. But instead of 2x, I have a 6x. So what would I have to do to 2 to get 6? Well, I'd have to multiply it by 3. So I'd actually have 3 du equals 6x dx. So now I'm going to go over and use substitution for this. And when I substitute in, and you can add your steps together, 3, that constant's going to be on the outside, and it would be the square root of u du. Because 6x dx is 3 du, so 3 is on the outside, 6x dx becomes du. And then my 1 plus x squared becomes u. Now, we want to write that square root as an exponent. So now I can use my power rule, and I would add 1 to the exponent to get 3/2, divide by that new exponent of 3/2, and plus c when I take my antiderivative. When I divide by a fraction is the same as multiplying by a reciprocal, so 3 times 2/3 would just be 2, u to the 3/2 plus c. And then we need to replace u with what we let it equal, so this would be 2 times 1 plus x squared to the 3/2 plus c. Let's look at example 4. Compute each of the following. So the antiderivative of 3x squared all over the square root of x cubed minus 2. So x cubed minus 2 is underneath the square root. So I'm going to let u equal x cubed minus 2. So du would be 3x squared dx. So my 3x squared all over the square root of x cubed minus 2 dx would then be du over the square root of u. This I could write as u to the negative 1/2 du, and then take the derivative. Add 1 to the exponent, divide by the new exponent. So that would be negative 1/2 plus 1 would be 1/2 divided by 1/2 plus c. This would equal, when I divide by 1/2, would be 2u to the 1/2 plus c. Replace u with what it is, and I would get 2 times the square root of x cubed minus 2 plus c. Let's go ahead and look at b. This would be the antiderivative of negative 4x all over 1 minus 2x squared squared. So I would let u equal 1 minus 2x squared. Take the derivative of u and the derivative of x, and I'd have negative 4x dx. So negative 4x all over 1 minus 2x squared all squared dx would actually be equivalent to, when I substitute in u, du over u squared. And this would be the same thing as u to the negative 2 du. Add 1 to the exponent, and I get negative 1 u to the negative 1 plus c. And since u, we need to replace that, I'd get negative u is 1 minus 2x squared to the negative 1 plus c. And we could finish that off and write it as a fraction. So I'd have negative 1 over 1 minus 2x squared plus c. And letter C, cosine squared 3x sine 3x. So we're going to go ahead, and I have a squared here. So that's like cosine 3x all squared. So I'm going to let u equal cosine 3x. So du would be sine 3x, negative sine 3x times 3. So negative 3 sine 3x dx. But if I notice here, I do not have a negative 3 inside my integral all, so I need to divide by that negative 3, and I'd have negative 1/3 du equals sine 3x dx. So here, I'm just going to go over and do my work here. I would have cosine squared 3x sine 3x dx equals negative 1/3 u squared du. Then I take the antiderivative, negative 1/3. I'd have u to the third all over 3 plus c. This would equal negative 1/9 u to the third plus c. Plug in what u is, and I get negative 1/9 cosine cubed 3x plus c. Let's look at example 5. Evaluate an indefinite integral by substitution. So we need to evaluate x over x squared minus 9 from 0 to 2. So the first thing we're going to do is we're going to let u equal x squared minus 9. So du equals 2x dx. But I only have an x dx, so that would be 1/2 du equals x dx. Okay, so we would have x over x squared minus 9 dx would equal 1/2, because that constant can be on the outside, du over u. Now I need to get my bounds, okay? And since this is in terms of u, okay, I need to find, instead of in terms of x, I need to find my u's. So when x equals 0, u would equal 0 squared minus 9. So u would equal negative 9. So instead of 0, I'd have negative 9. When x equals 2, u would be 2 squared minus 9, or negative 5. Okay, and then I can go ahead, and this would be the same thing as 1/2 from negative 9 to negative 5 of 1 over u du. And the antiderivative of that would be the natural log of u. So I'd have 1/2 the natural log of the absolute value of u from negative 9 to negative 5. So then I would go ahead and plug those in, and I'd get 1/2 the natural log of 5 minus 1/2 the natural log of 9. And using my rules of natural logs, this could become 1/2 the natural log of 5/9. And I can end there instead of making the 1/2 exponent. So with this, you need to make sure that you remember to change your lower and upper bound so it's in terms of u and not x, because over here it's in terms of x. Let's look at example 6. We want to compute each of the following. So the antiderivative of 6x squared all over the square root of 1 plus x cubed from 0 to 3. So the first thing is, let's let u equal 1 plus x cubed. Du would be 3x squared, but I notice instead of 3x squared, I have 6x. So I'd have to multiply this 3 by 2 to get 6x squared. So I'd have 2 du equals 6x squared dx. Also, I need to put my lower and upper bound in terms of u. So when x equals 0, u would equal 1 plus 0 cubed, which equals 1. When x equals 3, u would equal 1 plus 3 cubed, which is 28. So now, when I write this, I'd have 2, my antiderivative from 1 to 28 of u to the negative 1/2 du. Because you should have noticed that it would have been 1 over the square root of u du. And I can just write that from the beginning, the negative 1/2, since I'm going to use my power rule. Taking my antiderivative, I add 1 to the exponent, so that my first coefficient of 2 would tag along. When I add 1 to the exponent, it becomes u to the 1/2 divided by 1/2, and this would go from 1 to 28. When I divide by 1/2, it's the same as multiplying by 2, so this would be 4 square root of u from 1 to 28. So this would be 4 times the square root of 28 minus 1. And you can just leave it like that. If you really want to, you could rewrite it as 4 times 2 square root of 7 minus 1. But it's fine leaving it as the square root of 28, which is 4 times 7, and the square root of 4 is 2. The other one, we need to compute the antiderivative of x dx all over 1 plus x squared squared from 0 to 1. So we're going to let u equal 1 plus x squared. Du would equal 2x dx. And notice my x dx doesn't have a 2. So to get rid of the 2, I would multiply by 1/2. So I'd have 1/2 du equals x dx. Then we need to get our x values in terms of u. So x equals 0 in terms of u would be u equals 1 plus 0 squared. So u would be 1. And when x equals 1, u would be 1 plus 1 squared, which equals 2. So this would go from 1 to 2. Go ahead and put your 1/2 out front. And we'd have 1 over u squared du. This we could write as 1/2 from 1 to 2 of u to the negative 2 du. Add 1 to the exponent. I have 1/2. That would become negative 1, so we would have u to the negative 1 all over negative 1 from 1 to 2. This would equal negative 1/2 times 1 over u from 1 to 2. So we're going to go ahead and plug in this negative 1/2 we can have on the outside. I'm going to plug in my 2, and I'd have 1/2 minus 1 over 1. And this would equal 1/4. So now what I want you to do is I want you to go ahead and try to do the quick quiz on your own. So if the substitution, the square root of x equals sine y, is made into the integrand of the square root of x all over 1 minus x, the square root of 1 minus x from 0 to 1/2, the resultant integral is what? So go ahead, take a minute to try to do that, and then I'll give you the answer. The answer is letter C. So the answer is letter C. If you have questions on this quick quiz, please ask it in class or come to check-ins and we'll go over it.